Hello everyone. We're going to start odds and probability today, but before we begin that, we're just going to go over the questions assigned from last class. So starting with number 3. Alright, so number 3, Madeline is choosing fruit from a bowl which contains 3 apples, 2 nectarines, and 1 peach. If she randomly chooses a fruit without looking, what's the probability she will take a peach? So the probability of a peach, probability is always the number of favorable outcomes divided by the number of total outcomes. So the number of favorable outcomes in this case, there's 1. And the number of total outcomes, 3 plus 2 plus 1 is 6. So it's a 1 in 6 that she'll get a peach, which if you were to type that into your calculator, you'd get 0.16 repeating, or if you wanted to do that as a decimal, you could say something like that, 16.6 repeating. Okay, part B. She does take a peach, but decides she wants a different fruit, places it back in the bowl, then randomly chooses again without looking. What's the probability she'll choose an apple? So the probability that she will choose an apple, again, number of favorable outcomes divided by the number of total outcomes. This time we're looking at 3 apples, so 3 situations are favorable, and there's still, because she places the peach back in the bowl, there's still 6 fruits to pick from, so this reduces to 1 and 2. So it's a 1 and 2 that she'll choose an apple. On to number 4. Combination lock is made of 3 numbers between 1 and 3. So think of like the typical dial, the locks that you have. So it's a really simple one. You could have a 1, a 2, or a 3. You could spin it. You could have something like 1, 1, 1. You could have 1, 1, 2, that sort of thing. So there's, for each spot, there's 3 numbers to choose from, right? It could be 1, 2, or 3 there. It could be a 1, 2, or 3 there. And it could be a 1, 2, or 3 there. So given each spot, we have 3 numbers to pick at each spot. And the way we do this is we multiply the choices by each. So if there's 3 choices at the first stage and 3 choices at the second stage and 3 choices at the third, we multiply those numbers together. It's called the fundamental counting principle. Fundamental counting principle. So this would be, so 3 times 3 times 3, right, would be, come on, you can work for me. 3 times 3 times 3 is 27 possibilities, so come on. So 27 different combinations. Another way you can do that is write it out in like a tree diagram. So there's 3 possibilities for the first number, and supposing you started with a 1, you could branch out into, for the second number, 1, 2, or 3. And then for the third number, you could branch out further, 1, 2, 3, and so on. So each one of these would have 3 and 3. Okay, and you could do that same if you started with the number 2, and then that would have 3 branches, 3 branches, 3 branches, and then number 3, if you started with that, the next number could be a 1, 2, or 3. The third number would branch out like that. So each one of those would be 1, 2, or 3. So whichever route you take, suppose you wanted a 2, 2, 2, you would go 2, 2, 2. So each one of these, you count them up at the end. So 1, 2, so all of these should add up, well, they do, to 27. So each one of these paths that you can take covers all 27 possibilities. So the shortcut for that is just multiplying the number of choices by each stage. So that's how you do that. Okay, all right. The part B there, what's the probability that you'll guess the correct combo on the first try? Given that there's 27 possibilities, you can only take one of those possibilities. So it'd be a 1 in 27 that you would get that correct on the first try. Okay, next question, number 5. Teacher in Iqaluit is using markers to illustrate a lesson on a whiteboard. A box that contains 5 red, 4 blue, 6 green, and 4 black. What's the probability that his first marker he chooses will be blue? So there are 4 blue markers. Those are favorable. And 5 plus 4 plus 6, so 4 and 6 make 10, plus 5, 15, plus 4 make 19, so there's 19 total markers. And we should try to reduce that if we can. 4 over 19 as reduced as possible. So that would be fine as a fraction. If it wanted it as a percentage, you just divide that by that and multiply by 100, and you would get 21.1 roughly percent if you rounded it to the nearest tenth. Okay, part B. First marker is blue, does not replace it. What's the probability the next marker chosen will be red? So, okay. So he picked the first marker, it was blue. We're looking now for a red one. So probability that there's a red marker picked next. There are 5 favorable outcomes. And because we have removed 1 blue marker, there's now 3 there. So total markers left, 5 plus 3 plus 6 plus 4. There's now 18 markers left. 5 out of 18 is reduced as possible as far as fraction goes. You could write that as a decimal if you like. 0.27 repeating, that would be fine. Or as a percentage to the nearest tenth, you could say 27.7%. Okay. We'll do one more example with theoretical probability, and then we'll move on to odds and probability. Okay, question number 6. A standard 6-sided die has been rolled 5 times and landed on 4 each time. What's the probability the next roll will land on 5? So we have a standard 6-sided die, so possible 1, 2, 3, 4, 5, 6. Any one of those could roll on any go. So we roll 5 times. It happens to land on a 4 each time, so that's kind of interesting. But whatever it does historically, it doesn't affect our next roll, right? So if it happens that we rolled a number of 4s, we're not sort of due for a 5 on the next roll because it's totally independent, right? So each roll is independent. We're not owed a 5 because we've sort of stashed a few 4s. It's just as likely that we'll roll one of those 6 possibilities. So the next roll landing on a 5 is 1 out of 6. All right, onward. So odds and probability. So if someone says the odds of our team winning the hockey game are 3 to 1, what does it mean? So odds are similar to probability, but compare the number of desired events to the number of undesired events. So number of to the number of undesired events. So as a specific example, in the past 4 games, the hockey team won 3 times. The experimental probability is 3 out of 4, so we would see 3 out of 4 like that. Okay, the odds in favor of winning are a ratio of wins to losses, so we would write that as 3 to 1. So this is experimental probability. This is odds. So experimental probability we write as favorable divided by total. And then the odds we do favorable to unfavorable. So 3 times 1, 1 time loss. So if you add each of these numbers up, they add to 4 as they should. Okay, example 1. If you roll a standard 6-sided die, what's the odds in favor of rolling a 6? So odds in favor, right, if we start with the theoretical probability, there's 1 favorable outcome divided by 6 total outcomes. So that's the probability. All right, and then if we were to write the odds in favor, we write it like this. So favorable to unfavorable. All right, so the number of favorable outcomes, which is a 6, there's 1 of those. And the number of unfavorable outcomes, so that would be like a 2, 3, 4, 5, or a 1. There's 5 unfavorable, so that would be a 1 to 5. Okay, and then the odds against rolling a 6. So we are happy with either a 1, 2, 3, 4, or 5 in this situation. So we have 5 that we would like to see come up. So because we're doing odds against rolling a 6, and then there would be 1 sort of unfavorable outcome, which would be rolling a 6, so 5 to 1 in that situation. Okay, next. If a card is chosen randomly from a standard deck of playing cards, what's the odds in favor of it being a diamond? So if we bring up our deck of cards here, you can see in favor of it being a diamond, so those are the diamonds. There's 1, 2, 3, 13 cards here. So 13 favorable, and the rest are unfavorable. So there's 13 clubs, 13 spades, 13 hearts. These are all unfavorable. So if you do 13 plus 13 plus 13, that's 39. And you should try to reduce that if you can. So if you bring up your calculator, you do 13 divide 39, gives you that, and you can convert that to a fraction. It's 1 in 3. So we would write this as 1 to 3. Remember, favorable to unfavorable. Okay. Next question. What's the odds of it being against being a queen? So there are 4 queens in the deck, and we're wanting it to not be a queen. So there's 52 cards total. 4 of them are queens, so if we take that difference, 52 minus 4, so 52 minus 4 is 48. So there are 48 cards in this deck, you can count them, that are not queens. Those are the ones that we're interested in. Those are favorable outcomes for us in this question. So 48, and then the number of unfavorable, sort of, so we don't want it to be a queen, is 4. Okay, and we should reduce that if we can. So let's see. So 48 divided by 4, just 12. So if we divided each of these by 4, we get 12 to 1. So 12 to 1 are the odds against being a queen. Okay, I'll get you to try this assignment here, number 2 and 3. If you could just take a picture of that and send it through Edsby. I'll just do a check for completion and we're off to the races. Okay, take care.